start the colloquium with welcoming Artur. So the idea is that I'll read out your short bio a little bit, just as a politeness gesture, because this is one of those colloquia where this seems quite unnecessary, but then it'll be there on YouTube forever, that kind of thing. So Artur is already smiling at us. So it's of course especially great pleasure to welcome Artur Ekert to today's colloquium. So he's our colloquium speaker. I have been chasing him for this colloquium for 6 months. And so then it is, of course, amazing that it is still happening in 2021. So that is why it is an even more pleasurable event. So just a short bio, which I'll read out. So Artur Ekert is Li Kong Chian?
Li Kong Chian, yes.
Li Kong Chian, Centennial Professor and the founding director of the Center for Quantum Technologies at the National University of Singapore. He's also Professor of Quantum Physics at the Mathematical Institute, University of Oxford, which is in the UK. And of course, the big thing that excites all of us is, of course, he's one of the co-inventors of quantum cryptography, which is something we are very, very passionate about. And his current research extends over most aspects of information processing in quantum mechanical systems. He has worked with and advised several companies and government agencies. He is a recipient of several awards, including the 1995 Maxwell Medal and Prize by the Institute of Physics and the 2007 Royal Society Hughes Medal. In 2016, he was elected a Fellow of the Royal Society. And in his non-academic life, he's an avid scuba diver and pilot. So this is a very rare combination of quantum, scuba diving, and pilot. I don't think I've done this sort of an introduction before. So on a personal note, I have known Artur for a few years now and also had the immense pleasure of hosting him for a lab visit in 2019 when these things were actually possible. Little did we know that the next 2 years would be spent on Zoom, right? So that was one of those beautiful moments. So all of us in our lab were inspired by the visit and Artur's inherent simplicity and depth of vision. While we strive to make small difference to the world of quantum cryptography, of course, it is an immense honor and pleasure to host one of the founders of quantum cryptography for our Institute colloquium today. And of course, we look forward to hearing his views on privacy for the paranoid ones, the ultimate limits of secrecy. So Artur, the floor is yours.
Well, thank you, Urvasi. Thank you for your kind words and such a nice introduction. I'm a bit embarrassed, I have to say. I do have great memories from my visit to the Raman Institute and your hospitality and the whole, atmosphere around it was fantastic. So I do hope that we will get into the new normal in a not too distant future and such visits will be possible. But meanwhile, well, let's use this classical technology, shall we? I'll try to share the screen and see if I can talk about quantum. Right.
So Artur, while you do that, I just want to remind the audience that we have just discussed that Artur is happy with questions being asked on chat throughout the colloquium, because the idea is to be as interactive. And it's, of course, a great opportunity to be interactive with someone like him. And of course, in the end, we will have questions, just unmute and so on. But during the colloquium, it would be nice to keep it to the chat window, because then the flow is not lost. Yeah. So thanks a lot. Yeah. Artur, please.
Right. So this talk is going to be on a popular side. So I want this to be accessible to everyone. So it's more about the concept rather than techniques. But of course, there's lots of beautiful and interesting physics and mathematics behind. So for those of you who are interested, I'm happy to, well, answer questions if you have, and also point you in the direction of further reading. But this one is really, the talk itself is really to just convey the essence of quest for ultimate privacy. And first of all, whether it's, the question is it at all possible? And another question is it all about mathematics and mathematical ciphers, or is there physics there to play a role? And of course, I wouldn't be here talking about quantum if it were not for a very interesting side of quantum physics that allows us to pretty much achieve this goal. So if you really think about limits of privacy, and here I'm talking about more academic curiosity. Of course, there are government agencies, there are companies that are interested in this kind of thing, but for all practical purposes, the kind of security that I'm going to talk about is a little bit over the top. So it's like really pushing the whole field to the limits. But it's interesting, it's always good to know where the limits are, right? So that we can have a good reference point. Okay, so when we talk about security, privacy, and designing a perfect protection for information, we have to just acknowledge that there's been years and years and years, the beautiful history of inventions in this field. And it goes all the way back to ancient Greeks in Europe, and then Romans, and then people in different cultures and different civilizations had their own way to protect information. But essentially, as soon as humans came up with alphabets or kind of any written language, then a set of symbols to communicate, they became interested in modifying those symbols in such a way that only those who have access or privileged access and know a certain secret can read all those messages. But then when you ask yourself, well, is it then possible to design a cipher that is perfect, that cannot be broken by anyone, to come up with a method of communication that is resilient to any attack? If you were to take any guidance from history, then you would say probably, probably not, because every single time we had some ingenious method, be it a device, an algorithm, a way to encrypt information, sooner or later there was another ingenious method to break it. So you probably know about Enigma. There was really a very interesting and good and machine for cryptographic communication that was used during the World War II. But the machine itself was considered as pretty good, pretty almost unbreakable, until a bunch of Polish mathematicians managed to crack it, and then the British, based on the Polish work, kind of managed to read the Enigma communication, which had a big impact on the World War II in Europe. And then, if we talk about more modern methods of communication, there's the story is about code making and code breaking carries on. So basically, we still have a number of interesting examples how various ways of secret communications were compromised. Even with the modern ciphers that we use, the so-called public key cryptosystems, which are pretty good, and it's a beautiful mathematics, but the question then is, are they really secure? The security of many of them is based on something that is called computational complexity. And that means that we take certain mathematical problems and consider them difficult in terms of computational complexity. That means that once we ask when we take the best possible algorithm and try to solve that particular problem, the execution time or the use of physical resources usually grows very fast, exponentially, as the size of the input to the problem. So those are difficult problems, and we base our ciphers upon them. But at the same time, we cannot even prove that those problems are inherently difficult. Maybe they are not. And we have an interesting example coming from, say, factoring, where we know that a certain class of the factoring and discrete log are mathematical problems which can be considered difficult for classical devices, but if one day we have quantum computers, then they will not be considered difficult. So there is an issue with public key cryptosystems, and so I'll take you through to sort of quantum domain and talk about ciphers that we believe are unbreakable. But in order to explain why we believe they're unbreakable, let me just introduce the first basic concept, that is let's see whether I can just change this, which is a cryptographic key. So in cryptography, in secure communication, we try to separate sending encrypted messages from something that we call the key distribution. So if you ask if there is a perfect cipher, then the answer to this question would be yes, there is a perfect cipher. I can easily describe it to you how it works. But then there will be an issue with this, and the issue will be called the key distribution, and I'll explain it in a moment. So on this slide here, you see the perfect cipher. It's called a one-time path, and it works as follows. So imagine that, well, we have here two heroes, Alice and Bob, and they want to communicate with perfect security. So imagine Alice has a message, that the message is written as a sequence of zeros and ones, using some publicly known alphabet. It could be an ASCII code, for example, or something of that kind. So it's if it were sent publicly, everyone would be able to read and understand what it was. So then Alice has a random sequence of zeros and ones of the same length as the message. So you can, and we call this sequence a cryptographic key. It's written here in red. So what Alice is going to do is going to encrypt the message with a key. So we have two concepts here, two new concepts to those of you who are not into cryptography. The concept of cryptographic key, which is a random and meaningless sequence of zeros and ones. So there's no message there. It's just complete pure randomness. The important thing about the key here is it is truly random. It is as long as the message and it's secret, it's known only to Alice and Bob. So, and then the second concept is encryption. So that we take the message, combine it with a key. The way here we can combine it with a key is to do a simple addition modulo 2, which means that you take one bit from the message, one bit from the key, and add those two bits together. So it's like a binary addition, and the rule is that 1 plus 1 is 0. So that's the only difference from a regular addition. So when you add a message to the key bit by bit, then you realize that the randomness, which is sort of, I guess, intuition is quite clear here, that the randomness from the key is transferred to the cryptogram. So the cryptogram looks completely random because it inherited this randomness from the key. And then Alice is going to send this cryptogram over any unprotected channel to Bob. And whoever is going to listen to this or intercept this transmission will see only a random sequence of characters, zeros and ones in this case. But Bob has the key. So what Bob is going to do is going to pick up the cryptogram, pick up his key, and apply exactly the same binary addition bit by bit, and will reconstruct the message. So Alice added noise or randomness to the message by adding the key to the message, and Bob is going to subtract the same key from the cryptogram and recover the message. So this, by the way, is shown to be unbreakable as long as the key is random, the key is secret, and as long as the message, and never reuse. So you use the key once, and then you're not supposed to reuse it again. Then Claude Shannon managed to show that under those assumptions, you can assume that one-time path is perfect, is unbreakable cipher. No statistical analysis of on cryptograms will reveal anything about the message. So we have a perfect cipher. It does exist. The thing is, though, that there is a problem here, that if it is indeed the case that after every single message, we have to just drop the key and sort of the next message has to use a new fresh key, then there's a need to key generation, right? So the keys have to be generated at a certain rate. And that's fine if Alice and Bob can meet every now and then and sort of write down the sequence of zeros and ones and take them to their respective locations later on and protect them all the time. But if Alice and Bob are in two different locations and cannot meet, then they have to establish a very secure channel for the key distribution. So, and this is actually a big thing, because we don't know, on the classical side, we really don't know how to do that. How to make a channel, a physical channel here, that would allow Alice and Bob to distribute the sequence of binary digits and somehow guarantee a perfect secrecy. You see that the secrecy of of the one-time pad really depends on how good is your key. But if your key is secret, then you're fine. But if it is compromised, then the messages, of course, will be compromised later on. So the big thing is the key distribution problem. So this is like the thing that we want to solve at this point. Find a way to distribute a random sequence, completely meaningless, a random sequence of zeros and ones to two different locations in such a way that Alice and Bob have identical random sequences of zeros and ones, and they somehow can check that nobody eavesdrops, so nobody has any information whatsoever about those sequences of zeros and ones. So the so this is actually how the situation. If I were to sort of in one slide outline you the current situation, at least in our quest for perfect secrecy, then we know that a one-time pad is a good cipher. It's a perfect cipher. It has a key distribution problem. So how we are going to fix it? But there are two ways at the moment to say fix or go around the key distribution problem. One is a beautiful mathematical solution known as public key cryptosystems. So there is a way to bypass the difficulty by designing a system where you don't have just one key, but you have two keys, and one is private, another one is public, and there's essentially no need for the key distribution, except that those ciphers cannot be proved to be secure for the reason that I mentioned. They rely on a certain unproven mathematical assumptions of the that it is difficult to solve certain mathematical problems in a certain way. And the situation is even worse than it was before quantum computers showed up, because now we do understand that quantum computers in principle can be more powerful, and a huge class of public key cryptosystems is simply not immune to quantum attacks. So as soon as we have quantum computers, those ciphers will not be good. And so we have to, and this is actually an interesting and a topic that I'm not going to talk about. It goes under the label of post-quantum crypto, quantum resistant kind of security. The good question is, can we design a public key cryptosystem, so a purely classical system that is immune to quantum attack? And of course, there is an open competition, by the way, or the ongoing selection that is run by the National Security Agency. So now in the sort of the final stages, where there are some good candidates, but again, most of, even if we choose one candidate to be the standard for something that is believed as a quantum resistant, it will be extremely difficult, or rather impossible, to prove that it is indeed the case. Like it was with, say, RSA, it was difficult to prove that it is secure. We simply assumed that nobody knows how to deal with that because we couldn't actually prove that factoring is inherently difficult. So all those new ciphers will rely on certain assumptions that we cannot find at the moment a good quantum algorithm to tackle them. Whether will ever be the case forever, that's another open story. Anyway, so I'm not going to talk about this part. As I said, that this is actually a topic for another seminar or another lecture, even series of lectures. A very interesting and a very important area of post-quantum or quantum resistant cryptography. Very much of interest to people working in this field at the moment. But I'm going to talk about this, a way of fixing key distribution problem using quantum cryptography. So here we can literally fix it. We can say that there is a way to distribute random sequences to different locations in such a way that testing for certain correlations or certain properties, two people, the two recipients of those bits can actually make assessment to what extent those bits are secure. And here, essentially, there are two kinds of quantum crypto methods to do it. One can call it a prepare and measure, where you say, prepare certain physical quantum objects in certain states and measure in a certain way, or you can use quantum entanglement. So, so those labels that you may see in literature, like BB84, say E91, refer usually to who came up with the idea and when. So the Gilles Brassard and Charlie Bennett came up with an interesting way of doing key distribution, which which I'm not going to talk much about, because I want to actually take you into this device independence scenario, which is only possible with quantum entanglement. So it's not really that I'm just trying to promote the system that I propose. It objectively has a certain properties that makes it more interesting from the point of view of driving the whole field towards the limit of privacy. So I'm going to tell you a little bit about device-independent cryptography, which is where the kind of the frontiers of what we can do today are. So that's kind of the outline. Anyway, so so that's about the story about it. If you want to have a historical perspective on the quantum crypto, the solving the key distribution. So it originally chronologically started with Steven Wiesner, who had some ideas how to do it. Actually, he came up with an interesting scheme for producing a banknotes that cannot be forged, but then Charlie and Gilles translated this into a scheme for the key distribution. So that was this prepare and measure. And then completely independently, back in 1991, I came up with the idea how to use quantum entanglement and non-locality, and how to use Bell inequalities for testing the security. And so one can show that this prepare and measure approach can be reduced to entanglement based, but not the other way around. And we'll talk about it a little bit later on, perhaps. So let me start maybe now a bit more systematic explanation how quantum and what kind of quantum entered this field of secure communication. One can make a claim that back in the 1930s, so about 90 years ago, when Einstein was pondering upon the conceptual difficulties of quantum physics, if he had any knowledge of issues with secure communication, or perhaps any interest in secure communication, he could probably even come up with a concept related to quantum crypto. So at least, on my side, I took inspiration from this paper. So it was in 1935, Einstein, who was at Princeton at the time, was a grumpy fellow as far as quantum is concerned. He really thought that there were some deep conceptual issues, and then the quantum theory is a provisional one. And he came up with all kind of interesting ideas and paradoxes, and was challenging the people to come up with some kind of a reasonable explanation how things work. So this is actually a famous EPR paper written together with Podolsky and Rosen, where Einstein challenged the completeness of quantum theory, whether it really is the end, whether this is the ultimate theory, or is it something perhaps provisional that will be fixed at some point. Anyway, so in this paper, it's a beautiful paper. If you very brief, if you have time, just look it up and read it, because it is really beautifully argued. But what I found interesting as a student, when I was reading this paper, is there Einstein wanted to define a concept which he called an element of physical reality. And because he wanted to basically show that if we take quantum physics seriously, that there will be certain situations where we may actually question whether something exists, whether there's an element of reality associated with a physical quantity. And in order to make it more precise, he had to define it. So he defined it, and you can see in this box here, I highlighted that part. And what he did, he said, well, if without in any way disturbing a system, we can predict with certainty, so that is with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. So in other words, if you can learn about a property of the object without disturbing, so then this property is there, right? It's for real. But now if you're a crypto guy and read the whole thing, you think, hey, wait a minute, it's interesting, right? So this element of physical reality is defined in such a way that it defines almost a perfect eavesdropping. It defines what bad guys want to do when they want to intercept communication. They want to learn the value of the physical quantity. In this case, it will be like 0 or 1 encoded in something, let's say polarization of light or so, without disturbing it in any way. So if it's not disturbed, the two users, Alice and Bob, wouldn't actually know that any eavesdropping was taken place. So if it is indeed the case that you can attribute this element of physical reality as defined by Einstein in this paper to objects all the time, then of course there's always a possibility for eavesdropping, at least at some abstract fundamental level. So, but at the same time, for me, knowing what happened later, I knew that it was then possible to design situations or scenarios where there was, you can show that there's no physical element of physical reality as defined this way. And so then perhaps this is a situation where a perfect eavesdropping is not possible. So that's like, you know, hint, a kind of intuition that came from a piece of scientific writing was referring to something else, right? So Einstein was talking about philosophy of science. He was concerned about foundations of physics, foundations of quantum theory. And if you read it with from a different perspective, with fresh eyes of someone who's interested in secure communication, out of the sudden, the same sentence has a completely different meaning to you. So let me then just describe the whole thing. Hello? Is there a question?
Sorry, Arthur, I have muted the individual.
I see, okay.
Yeah.
I couldn't actually hear clearly.
I think it was not meant for you. Sorry about that. Yeah.
Okay. So here's a simple situation. So I would like to, you know, in a popular talk like this, it could be sometimes, you know, I just always have this impression it's superficial and so on and so forth. So at least I would like to explain maybe one thing in detail. So if you, and this one I think is kind of interesting and simple to explain. So if you want to take one thing that is not necessarily crypto related, that would be this part about the Bell theorem. So it goes, the line of argument goes like this. Think about the polarization of light, okay? You know, light is made of photons, so think about the polarization of a photon. So it's an intrinsic property of a photon. So, and moreover, there's not just like one polarization, but there are many of them, and you can define a direction along which you want to measure polarization. So, so we measure, but we can measure polarization with respect to some specified direction. And if we do that, for every single photon, we can design a measurement where we can get two outcomes and only two outcomes, say +1 or -1 in the units of h bar, right? So then polarization is along a particular direction is a measurable property. So now the question is the measurement uncovering pre-existing value of this polarization? So that's the classical way of thinking, right? So measurements uncover pre-existing values of whatever we measure. They are there before we perform this measurement. So in this particular case, we just simply assume that we can choose the direction and measure. And then one way of thinking, of course, is that the polarization is there. The photon is carrying the values of polarization with respect to any direction whatsoever. So that's so in this sense, the value is predetermined. However, as you know, Einstein and people later rephrase this argument, that there may be situations where this argument doesn't quite work. So I'm going to show a typical example of the so-called entangled photons, which doesn't for those of you who are not in this field, doesn't really matter. But the situation where two photons are generated and they do not have predetermined values of polarization. So that's let's look at the situation. So that was actually the interesting insight that came from John Bell. So remember, it was 90 years ago. It was Einstein EPR paper, and about 60 years ago. So it took about 30 years between those two interesting papers, one by Einstein, Podolsky, and Rose, and the other one by John Bell from CERN, where John Bell said, well, look, it's not actually completely a philosophy on the Einstein side. Actually, that kind of argument that Einstein put in the paper can be translated into something that is a testable proposition. So what you can see here is John Bell in his office at CERN. By the way, he was working on particle accelerators. So his job was to actually build and design those accelerators. And he was essentially doing all these foundations of quantum physics after hours. So that's the funny thing is that these days, he's really known for his contribution to the foundations. So sometimes, you know, what you do after hours may matter more than your day job. So here you can see, apparently I understand this picture was taken when he was discussing with Alain Aspect in about 1964 in his office at CERN, a potential experiment. And so let me describe, so you see on the blackboard, you see the outline of the experiment, and but let me just try to explain it in perhaps a simple way. So here's the concept behind this experiment. So remember, we want to show that there may be situations where we have two photons, we have a pair of photons, they come from a source, and we want to show that there may be a situation where we cannot attribute values to polarization with respect to certain directions. So our Gedanken experiment here, the thought experiment is that we have Alice and Bob in two different locations. We have a source of those pairs of photons. One photon goes to Alice, another photon goes to Bob. Now, Alice can choose between two different types of polarization. So we are talking about choosing two different directions. And we call them A1 and A2. And Bob can also choose two different types of polarization, call them B1 and B2 on his side. And they're going to, for each incoming photon, they will measure either A1 or E2, choosing randomly. So Alice is going to have some kind of a random number generator or a free will, and it will switch to either A1 or A2. And for A1, she can get two outcomes, +1 or -1, and the same for A2. And likewise for Bob. So B1 has two values, either +1 or -1, and B2, again, +1 or -1. So you may think at this point about A1, A2, B1, and B2 being binary random variables having numerical values. So now we are making this assumption, right, that if A1, A2, B1, and B2 correspond to different values of polarization, so that we are making now the assumption that those values are there prior to the measurement. So if you take this view and then you construct another random variable, and it's actually very simple. So you look at this random variable S, which is a linear combination of products of A1, B1 plus B2 plus A2 times B1 minus B2. So if A1, A2, B1, B2 can only take values plus or minus 1. So you can see that S can only take two values, which is plus 2 or minus 2, right? Because the term in the brackets, one of them has to be equal to 0. So for each incoming case, if you consider different instances of this experiment, then in each instance of the experiment, then the terms in the bracket, one of them, if say B1 is equal to B2, then the second term will be equal to 0. And if B1 is different from B2, then the first term in the bracket will be equal to 0. So S has to have can only have two different values, plus 2 and minus 2. And then if Alice and Bob run this experiment many, many times, so they register the values A1, A2, B1, B2, and then they can then estimate for each run of the experiment. They can just so in sort of, if they run it many, many times, they can estimate simply the average values of all the 4 terms that you can decompose S. So the average value of S can be calculated, in fact. And if you get the average value, so clearly it has to be somewhere between minus 2 and 2, right? So it's if S takes values plus or minus 2, then sometimes it will be plus 2, sometimes minus 2. So the average value is somewhere in between. And this statement here, as simple as it is, it just can be demonstrated or simply explained in one slide, is a statement that we call the Bell inequality or the CHSH inequality, or it is actually quite a profound statement about physics. So, and it wouldn't be actually very profound, but probably many people look at that kind of expressions in the past because it's kind of trivial, right? And it's a statement about classical probabilities and assuming that the values do exist, right? So that's what is interesting though is that this S, which the common sense tells us has to be between minus 2 and 2, can be actually greater or smaller. So it can be greater than 2 or smaller than minus 2. So the average, the absolute value of the expectation of S can be greater than 2, and that is actually something that is surprising. So and I don't have to go perhaps through this slide, but if you look at the quantum predictions for this kind of experiments, and quantum at least at the instrumental level gives you probabilities that are different and correlations that are different than classical probability theory. So you can show that the value of S can be as large as 2 times square root of 2, right? So it can go above 2. And then the question is, what does it mean? And first of all, is it true? I mean, that would tell us something really profound about reality, that those values are probably not there, that at least one of the assumption that we were making, that we can attribute numerical values to A1, A2, B1, B2 is probably not true in this case. So, and here we have to just talk to our experimental colleagues because there's no other way, we can argue and argue, but we have to do something about it. So here comes experimental realization. So as I said, this was you could see actually those two in John Bell's blackboard. You can see those two different values, the upper bound on classical correlations, which is just 2, and the quantum mechanical version, which means that it can go all to square root of 2. And there are many experiments, and some of them predated Alain Aspect experiment. I'm just showing Alain Aspect because I think that was one of those most convincing. Those people who were interested in the foundation. Not so many people were actually that much interested in that thing. You may think, well, how come this so profound, so fundamental, but somehow the field of experimental verifications of the Bell inequalities was not that crowded in the early days. So Alain Aspect was probably one of those first who convinced the community that indeed the Bell inequalities are violated. So you can have this figure of merit S greater than 2, for example. And that was a beautiful experiment at Institut d'Optique in Paris, in Orsay, actually, in 1982. So here we are. So we now, of course, there was a follow-up. There are many experiments today. So today we have we are pretty confident that the Bell inequalities are violated. So that means that we can create the situations where particles and physical objects do not have predetermined values. So in particular, we can create the pairs of photons that don't carry predetermined values of polarization. So now intuition without mathematics tells you that if the values do not exist prior to measurements, they are simply not there. They are not available to anyone, including eavesdroppers. So there's nothing to eavesdrop on because the values do not exist. So in a way, now testing for the violation of Bell inequalities can be viewed from a different perspective, from the crypto perspective, as a test for eavesdropping. So that was, that story that one can, that requires, of course, translating the experiments that look for the violation of the Bell inequality into quantum key distribution. So where you send photons into 2 different locations, you explore perfect correlations, but you also test for the Bell inequalities just to make sure that nobody touched your photons, so that they were not simply measured prior to your measurement. And that can be done, of course, and that has to be sort of supplemented by error corrections and privacy amplification. So there are many other techniques, mathematical techniques, that cryptographers use. And so I managed to translate it into a quantum key distribution based on Bell inequalities. And as I said, I'm not going to go into technical details. There are basically 3 ingredients there. The first one is the violation of Bell inequalities, then other techniques. You may ask the question, okay, usually it's not always the case that if you simply have 2 square root of 2 violation, then there are sort of, the CHSH violation could be actually smaller than that. So you have to estimate how much of the secret key you can extract from given a such and such violation of the Bell inequality. And again, it just requires a little bit of fiddling, but mathematical gymnastics, but that can be done. So now given that it was possible now there was sort of like a possibility based on the Bell inequalities to show that there could be a secure key distribution. Of course, one can say, well, in this case, you can just take all those experiments where you saw the violation of Bell inequality and reinterpret them in different way. Well, that's kind of, half true. You have to actually have a dedicated experiment where you just think in terms of the key distribution as your scenario and focus on certain other things. And I was working in the early days, I was working with 2 colleagues of mine that I should mention, with John Rarity and Paul Tapster, who used to work for what used to be called Defense Research Agency in Malvern, not far away from Oxford, where in the early 90s, we managed to demonstrate that this quantum key distribution really works. There are all kind of interesting anecdotes and funny stories associated with this. This was a Ministry of Defense establishment. But for some historical reason, people in working institutions which were under the umbrella of Ministry of Defense were not supposed to be working on crypto. Crypto was under the Foreign Office, and there were another agencies that were supposed to be working on crypto. It took a while to persuade the management, the senior management, that actually the other agency may not have sufficient knowledge about quantum, and it's perfectly okay to do this kind of experiment under the umbrella of Ministry of Education. So as you can see, the admin, senior managers, or middle management is exactly the same all over the world. Anyway, so okay, so the first part of the story is almost done, right? So I told you how you can use Bell inequalities to establish security of the key. And that was demonstrated, and then people started thinking how to implement that. And so let's look at the assumptions. Remember, here we are just purely on the academic side. We are interested in not so much, can it be done right away? Can it be built? Can it be solved? But what are the assumptions there? So first of all, the obvious assumption is, of course, that Alice and Bob have secure labs. So once they measure things, that their devices are protected, nobody can actually look inside. We also assume that Alice and Bob trust the devices, so that they, of course, they have stuff that they know what the stuff is doing. It seems like obvious, right? So they constructed those devices, or they purchased those devices that measure polarization, and when they set up measurement for polarization A1 or A2, or B1 and B2, then the devices are really measuring those types of polarization. So there was this assumption that seems kind of obvious, but there was an assumption of that kind. And of course, we also assume that Alice and Bob have kind of free will or random number generators that they can choose observables A1, A2, and B1, B2 randomly and independently from each other. So it's actually quite important for being able to test those Bell inequalities. Now, can we do something about any of those assumptions? So let's look at the second. Can the Alice and Bob control and trust devices in the lab? So sometime after, I came with this idea of the quantum key distribution based on Bell inequalities, a few colleagues of mine pointed out that actually the Bell test is rigid. And here is just, departure from other method of secure quantum key distributions, like prepare and measure BB84 or something. So the Bell test is rigid, and what that means is that if you move with the value of S from the classical domain, you pass this border 2, and then you just go to, say, 2 square root of 2, which is the best you can do from on the quantum side. So this one is known as a zero-sum bound. So when you are at the extreme, if your S is equal to 2 square root of 2, then there's no any other way to get it but through the measuring that kind of polarizations on entangled photons. So it goes the other way around. It basically says, if you see this value, there's no other experiment whatsoever, or the experiment that you have to perform in order to get this value has to be of the type that you measure kind of quantum bits that could be in disguise, but essentially it's equivalent to measuring entangled quantum particles. So if you see this value, there's no way anyone could do it in any other way, which is actually a very strong statement, right? So it just goes the other way around. So that means that if you see this violation at this level, you don't have to actually worry about devices, because there was no other way. It had to be done in that particular way. So those devices had to be doing measurements of CHSH type on highly entangled particles. And that actually gives another interesting twist to the whole story that is known as a device-independent crypto. We don't have to worry about devices at this point. As long as we see this violation of Bell inequalities at this level, then that kind of certifies devices. It means that those devices are fine. So you may think about a scenario that you get your devices from a source that you don't trust. But if the devices deliver this kind of correlation, 2 square root of 2, then they're fine. You don't have to even know what is inside. You don't care. Isn't that amazing? You don't really care what is inside. Or even in sort of more, perhaps a better example is that sometimes, you may want to build those devices, but you don't trust yourself. You may make a stupid mistake. And so the question is there no fault in your design? Can you be absolutely sure that you haven't messed up something? So again, this level of correlations will tell you, no, that's fine. You haven't actually sorted out anything. Those devices are doing CHSH measurements on highly entangled particles because there's no any other way to do it. And so that was, sometimes I was nicely surprised that this implication goes that way. And so I wish I could say, I thought about it, but I didn't. So sometimes your ideas are more clever than you are, and this is one example. But a number of colleagues like Tony Yassin, Nicolas Brunet, Nicolas Gizin, Serge Massara, Stefano Pironia, and Valerio Scarani came up with this idea and the proposal, how to drop one assumption there. So the whole scheme becomes much more secure. There is a price to pay, though. That the key rate is, so this is the red thing, is not as good as it is in the case of when you know your devices, but that's a price to pay. It's still pretty good. So yeah, sure.
Yeah, so it says QKD aims to solve the potential threat of the power of quantum computing to existing security protocols. Given that we can have quantum resistant, that is post-quantum or quantum safe crypto protocols implemented with a fraction of investment needed for practical QKD, is QKD implementation currently for the next 30 to 50 years only of academic interest? Even if we make the investment for a worldwide quantum internet, the current eavesdropping methods that attack authentication rather than encryption would still be a threat.
Yes, so okay, so maybe I'll just this is a good question, of course. I will talk about practicalities at the end. So let me just defer this question. I will answer this question in like 2 or 3 slides, okay?
Okay, and there is a further addition to that. Even with Bell inequality violation, one can still have quantum interpretations with element of physical reality, although non-local like Bohmian mechanics. Also, superdeterministic local theories are not ruled out by Bell inequality violation.
Yeah,
in this context, can our understanding of nature improve in the coming decades? We may conclude one of the 2 above interpretations is correct, which would remove the bias of basis of security proofs of quantum cryptography. Is it too early to build the infrastructure for QKD beyond academic interest, given there is no immediate threat? So it's, of course, a follow-up to the previous one. So it's
a very good question. So I will, it's sort of like in anticipation probably of what will happen later. I will just also address the second
one. Great, yeah, thanks.
So just bear with me, just 2 more slides, and I'll be answering those questions. So the big thing, though, about this device-independent thing was that the key rate that was originally derived assumed that those in the case of independent and identically distributed kind of scenario. So what that means, it was assumed that each run of the devices is independent and different from the previous one. But now, that's kind of silly to assume, right? Because now we want to talk about the device independent scenario, and we are saying, okay, we don't even know what is inside. So it could be that the devices are operating in such a way that the end action depends on all previous actions of the device. So there could be a history built into this. And it doesn't have to be what is known as IID scenario. So therefore, even though the idea was proposed and the key rate was deriving this under this IID assumption was simply no good to persuade the world that the device independent actually makes sense. Because you make very unreasonable assumption. Why an eavesdropper would give you this privilege of design devices that you receive from enemy in such a way that they work in this IID scenario. Well, so the good news is that the proof actually is fine. So there was a beautiful piece of work by those three people that you can see the smiling faces on this picture. So that's Renata Renner at the top and Thomas Vidic, and last but not least, Rotem, Rotem Arnold Friedman, who actually managed to come up with something that is called entropy accumulation theorem, EAT, which allows to reduce all those most general strategies to pretty much to IID cases, and so simplify the security proof immensely. So that's from, that paper basically shows, yes, that the quantum device independent scenario makes sense. Now then we come to the point which was touched upon one of the second question here. Okay, so let's look again at those assumptions. So we now managed to say, okay, the first assumption is that no information leaks from the labs. The second one we fix, right? So that Alice and Bob do not have to trust the devices. They can get those devices from anyone. But, Alice and Bob, we still made this assumption that they have a free will because they have to run this bell test on the devices. So it would be a silly thing to do is to take a random number generator from the same source or from the same kind of a person that provided you with those devices. So you'd better actually have either your own random number generator or have something that you can trust, or purchase this from sources that you can trust. So the element of trust, which we want to get rid of completely here, still remains and it's sort of, it's resting with those random number generators of free will, if you wish. So, and here comes the thing, that this, whoever was asking the question referred to, it is still the case that even with the Bell inequalities, we cannot rule out a super deterministic scenario. So it might well be that everything, absolutely everything, is predetermined. In this case, if Alice and Bob do not have a free will and do not have truly random or at least a little bit of randomness in their devices, then both at the fundamental level we have a super determinism, and then in the crypto scenario we just have a situation where Alice and Bob cannot construct a system where which they can claim that it's completely secure, that Eve simply can have access to this. But of course, one that raises a very interesting philosophical question. In a super deterministic world, whether secrecy makes any sense, it's another interesting story. Yes, there are other ways of looking at perhaps the violation of Bell inequality, and certainly it is certainly the case that the violation of Bell inequalities doesn't give you a decisive answer about the existence of truly inherent randomness in the quantum world. It simply tells you that, there are assumptions, and one of those assumptions is that Alice and Bob make those free choices, and so they can choose the observables, or they have a good random number generator. So in a way, there is an interesting work how to amplify quantum randomness. There is a randomness amplification, but you have to have at least epsilon of this randomness. If you don't, if it's all super deterministic, then the whole scheme doesn't work. So the last thing, is just we need a little bit at least of this randomness in order to claim that it's all secure. Now let's then address and this will be sort of trying to address to some extent the first question about the practicalities. So the first thing to say is that quantum crypto is practical. It's be it in the form of BB84 or entanglement based. Usually the entanglement is a little bit more difficult to implement, but doable. And it's implemented in a spectacular way, both in many places, as over optical fiber on the ground, but also there is an interest of the key distribution from satellites. So it's and the technology is really pretty good. So one of the most spectacular, I think, before I just tell you about the most recent one, the Chinese experiments, one of the most spectacular thing to me was when a colleague of mine here in Singapore, Alex Ling, and his collaborators were working on a little CubeSat, small satellite with a source of entangled photons, and they wanted just to put it on one of those supply rockets that takes it into the orbit, so releases the satellites there. So as it happened, one of these early experiments that was not entirely successful. So simply, not because they did something wrong, but because the company that was sending those satellites into the orbit. So there was this supply rocket called Antares that exploded. There was a spectacular explosion in 2014, and we lost the payload. And so that was like, oh no, okay, that's a disaster. But the funny thing is, there's never such a thing like a total disaster, because the debris was sort of searched, and the equipment and this piece of equipment that was designed by guys in Singapore, in this company, by the way, called Spectral, was still in working order. So it just survived the whole explosion, and that showed that the stuff is really, really robust. It also works. And probably, as you heard, the most spectacular technical achievements are probably, well, almost certainly by the Michel satellite. There's a dedicated Chinese satellite that demonstrated the key distribution over thousands of kilometers on the Earth. But there are technical challenges. I don't necessarily, if you want, I can go to them. With the bit rate and everything, and the final statistics on the key recovery and so on and so forth. So that actually brings me to the first question. So given that we can work on post-quantum crypto, is it then justified to put so much and lots of effort into a quantum crypto? The thing is that the post-quantum crypto will still have a status of security based on computational complexity. So that's the idea. So we may come up with a new mathematical problem, be it lattice-based crypto, and then we will simply have to assume or believe that nobody will find good quantum algorithm that will actually handle this lattice-based crypto. So there is a bit of there will be no security proof per se. Now, and so it makes perfect sense actually to have a combined system where a hybrid system where we also pursue more reliable directions. So basically, on the practical side, you see the way I presented the whole challenge of quantum key distribution, I was talking about one-time path. So you may think that you really need long keys and so on and so forth. So in theory, yes, but in practice, the most secure non-public key encryption, like AES, for example, requires, if you really, the key could be of the order of, well, if you really want to go to 256 bits or something like this, you can, and then you have really, really non-public key, well-established crypto protocol. So then you can either use quantum crypto or some form of a public key encryption to do the distribution of those keys, but then those keys are recycled in those devices, and you can send probably a terabytes of data before you need another key and so on and so forth. So it's not the case for practical crypto. It's not the case that you need lots of these bits. So it makes perfect sense to experiment with the key distribution to use in those crypto devices, not in one-time part. One-time part is extreme. If you really want to be paranoid, yeah, you can do it, but there are, you can basically use it in more conventional secure devices, which are cryptographic standard like AES. So the so that's kind of a maybe not exact, but that's the kind of answer to the first question. Now the to conclude this, I think that to me, I have to say, well, it's been, you know, it's been some time, right? So it's been like 30 years almost, and I just think, gosh, you know, it's from 1991 to 2021. I never expected that this idea that was part of my PhD in Oxford that will actually ever be realized. You know, I thought at the time, well, you know, just you have to write your PhD at some point, right? So just write it and just move on and do something useful. So I tried to do something useful, but every single time after that, I was just brought back to quantum crypto this way or another. So it was interesting to see how it evolved, and it was quite unexpected, I have to say, from early wacky ideas in 1991 to all these experiments, say in China, where you have a distribution of quantum key using entanglement-based crypto over 1,000 kilometers underground or so. So it's actually quite nice. Now, if you want to read a little bit more about it, so it's still sort of a semi-technical, semi-popular article that I wrote with Renata Renner some time ago. It's a review paper in Nature that I can recommend. But other than that, there's, of course, you can just Google around and lots of fantastic explanations. And you know, it's also good to know that in India, the Raman Institute, of course, in particular, there's a serious effort to make quantum crypto happen. So I don't think I will talk in much more. I think if there are any questions, I'll be happy to answer them.
Great. So thanks a lot. That was a very, very enjoyable colloquium, and I'm sure it was for everyone else as well. So we had already a question on the chat window, which Shorodip, did you want to unmute and ask yourself? And we can do the same for others. Yeah.
And the question is, you have talked about the assumption behind bail-based crypto is the no information leaks assumption. So my question is, are the no information leaks and the locality assumptions the same? In a sense, how one can ensure that no information is leaking from their lab, whether they need to ensure of closing the locality loophole or not? I mean, how are those assumptions connected or not?
Yeah, so of course, you know, yes, so you're right that in a scenario where you get devices from a completely unknown source, right? You cannot exclude also a situation that there's unknown to you a transmitter that transmits information from those devices to an eavesdropper, so an eavesdropper constructed. So yes, indeed, that is a consideration. So probably a more realistic scenario to think about the device independent is that you build those devices, and devices are built by trusted people, and you use the device independent of this reverse implication that if you see those good correlations, therefore it works as it should. You simply use it just to make sure that you haven't made any serious mistakes. So that in your design, it's just proof. So you haven't actually made something stupid. But of course, you know, you're right that buying black boxes is just a little bit. You of course, you know, there are ways of monitoring for known side channels of some sort, but that wouldn't usually work if you want to take it to the extreme. So therefore, if you think about practical applications, the best way to go is to have those devices built by well, certified or trusted entities. Obviously, they would not put a transmitter there because you trust those guys, and the other, but the correlations, Bell inequalities will just guarantee that there's no like system design failure of some sort in the building of it, so which is great. In general, any other side channels that apart from the one that you mentioned, any other side channels are excluded here because with the side channel you would also see the drop in the quantum correlations. But this one, exactly this one that you mentioned, that implementing transmitters that somehow use some maybe unknown physics to a given or something so spectacularly high tech that you cannot detect is a theoretical possibility. So that's why you would rather do those devices yourself or someone whom you trust.
Okay, so
okay, just one more.
Yeah, okay.
Just one more statement. That means if one ensures that there is no locality loophole, then the no information leak assumption is already addressed. I mean, when Alice and Bob are doing Bell experiment, if they ensure that there is no locality loophole, then automatically no information leaks assumption is addressed.
Yes, so of course, we have to make sure that those Bell inequalities perform without any loopholes. You're right. So there's a question of detection loophole, there's a question of locality or non-locality loopholes. So both of them have to be addressed. In this case, we can also we have to, unlike in the case of scenario with trusted devices, in the device independent scenario, you have to be very careful about the efficiencies of your devices. So it's easy to construct attacks where the device simulates no response. So it's like a detection failure of some sort. And one can easily construct attacks where detection failure may actually be premeditated or pre-programmed in a certain way. So there are serious requirements. So therefore, we don't have any experimental demonstration of the device independent, even though there are some interesting work, but those are not with photons at the moment. There are people in Oxford who are playing with, want to demonstrate the proof of the principle using entangled ions, but that's not in a crypto scenario at the moment.
Any further questions or comments? Anyone else?
Yeah, Artur, can I?
Yes, please.
Make a comment? And in view of the randomness issue that is involved in whatever you mentioned, this Pironio work of 2010 showing how Bell's theorem can be used to generate random numbers. And then this demonstration by Cavalcanti, Weisband, that one can derive Bell from assumptions at the statistical level, predictability and no signaling, using them to generate what they call genuine random numbers. So would you like to comment on that how that can be useful for plugging that randomness loophole, if I may put it there?
Yes, of course. You may use quantum phenomena, the one that you mentioned, and randomness expansion or randomness amplification that was proposed by those people to increase the amount of randomness that you have locally. And that can be done, but we also have a statement that there has to be at least epsilon randomness in order to expand this randomness. So that still the super deterministic scenario where there's absolutely no randomness whatsoever is still a possibility that we cannot exclude. But the good thing, just to cut a long story short, if I can just maybe trivialize it, that work that you mentioned shows that if we can have a little bit of randomness locally, then there are ways to amplify this randomness. So that's a good thing. There are ways we can have plenty of randomness from a seed. So the randomness expansion, randomness amplification is a good thing that we can use. And so we managed this last assumption really is sort of almost, you know, okay, except that we need this epsilon of randomness to do something, and therefore I think it is a valid comment that was made that in the super deterministic scenario the system wouldn't work, and we have to exclude. I think it's very, you know, it's of course it depends on your philosophical belief. Is the word super deterministic or not? I don't know. I believe it isn't, but well, okay, one can talk about it just in all kind of ways, but I think in this particular context, there is this set of measure zero, I would say, of possibilities of superdeterminists that quantum crypto wouldn't work, even though if we take into account that work by the other guys.
Can I ask a more practically motivated question on satellite QKD, since you touched upon that towards the end? And so you said that you're happy to discuss numbers and so on if people are interested. And that's something very interesting. So, I mean, you know, in satellite QKD, do you have any, I mean, of course, E91 is an entanglement-based protocol, but then do you have any reason to believe that there is an advantage or disadvantage of E91 over BBM92?
Well, if you, not necessarily, I mean, you can use satellite key distribution in all kind of ways. You can you know, talk about downlinks, uplinks, and so on. It's very pleasing, of course, to be able, if you have good technology, to be able to point your entangled photons into two different locations and establish the key there from one location of the satellite. So that is fine. But the problem in general with satellite communication, no matter which particular system you use, is that the data rate is relatively low. And so first of all, you know, you have only a finite time window when the satellite is just passing over the ground station to receive data. And then sometimes it's not even possible because the weather may not be good enough. So then you don't get the clear sight. Usually it's estimated like in places around here, only 20% of the passes would be good enough for communication. But, you know, over a year, you may have something like 150, 170 of those passes. So you can accumulate probably, even if you are conservative, you can get something like good number of kilobits within a year, and having in mind that you want to use it probably for devices, this key distribution using the conventional method like AES, for example, they require 200 bits as a seed key, and then that is of course recycle, and from that you can get about maybe terabyte of communication before you have to do it again. So it should be probably okay. But but again, if you want to be, you know, in our line of business, we want to show that it's absolutely secure. So the problem is that in this narrow window, you don't get that much data, and therefore many of those analyses that you have go into the asymptotic regime, right? So you say, oh, in the limit of infinitely long keys, you have all those entropies and so on and so forth. So here you have finite data, and you have to be a little bit careful of it because there's a margin, and then this finite key analysis in this case, and to show that this is really a secure thing, it is not a trivial issue. It is being addressed, and I just showed some references there. But you're right. So it's, and it doesn't really matter that much whether you use entanglement or BB84, but it will, the same things will be a problem, the data rate.
Right. So anyone else had a question? You can just unmute. Sarkan 8. Yeah, sorry.
Yeah, hi. Yeah, hi. Can you hear me?
Yes, I can hear you.
Hi, thanks for the great talk. I want to ask a question about the light sources. whole quantum cryptography studies or cryptology studies also encourage a lot of research on efficient light sources like entangled photon pairs or single photon sources, but it looks like that the QKD is dominated by mostly entangled photon pairs. So what do you see about the kind of future of single photon based QKDs? So that's my question. Thanks a lot.
Right. I wouldn't say it's dominated. The experimental side, I think, is still dominated by prepare and measure because it was easier to do, and there are all kind of variants of it. So I think that it's only more recently that we have better sources of entangled photons and we can use them. There is a motivation, of course, this device independent kind of scenario, which would be nice to demonstrate. But sure, certainly the quantum crypto has some niche impact on building better sources of both entangled but also single photons, and also on the detection side to build a better detectors that have to satisfy a certain criteria if you want to use them for quantum communication. So they have to be very efficient, of course, because, for example, if you don't have efficient detectors, then forget about going even in the direction of the device independent. You also have to have them responsive with a given sort of a time frame and so on and so forth. So there are many of issues that you have to tune those detectors to make them good. And that certainly created a small community of people who are working on improving those devices. I'm sure that my experimental colleagues will have much more to say about this, but I do know that this is sort of a technology that is being improved for the purpose of quantum crypto as well.
Okay,
and
so,
in particular, even I just need to add this, it all depends, there are all kind of technical specifications that come into this game. If you want to have quantum key distribution over optical fibers, you are usually restricted to a certain wavelength, like 1.3, 1.5 microns, which is sort of a telecom wavelength. And you want to have good detectors in that particular frequency range. If you talk about satellite communication, you may want to go to these sort of lower wavelengths because of the transmittivity in the atmosphere. So the range of problems here is not only good sources and good detectors, but it's also a question in which range, for which wavelength should they be, because it's not, it's not a big deal to have a good efficient detector for very high energy stuff, which means a very low wavelength, like high frequency, because the photon will carry lots of energy there. But if you go into a single photon detection in the other direction, then it is a challenge. But there is technology is progressing there. So I think over this last few 10 years or so, there's been amazing progress in better and better detection and better sources of photons.
Any last question from a comment?
Can I just
Yes,
utter
please.
one more quick question? You, in your Scientific American article, Beyond the Quantum Horizon, you remember your article Beyond. So there you had speculated that means going beyond the quantum mechanical considerations may give new kinds of computational power, but what kind of implications it would then have in the cryptographic security context? Means what kind of, for example, if the reality thing is compromised, means you have some kind of model like the Bohm model to be true. Suppose, for example, Bohm model is found to have some ramifications different from quantum theory.
Right. It's difficult to say. I think that I think in that article that you mentioned in Scientific American that I wrote with David Deutsch, we speculate about a situation where you cannot build a quantum computer for a good reason. And the good reason being that you discover something profound about nature, right? So the question is, at the moment, there's lots of hype and enthusiasm about quantum computing and building quantum computer and so on and so forth. And of course, it's nice if people can build a quantum computer, but I think, and then we believed, David and I believe that it would be even more interesting and more fantastic if you couldn't build a quantum computer for a good reason. Because then you would discover something very profound, because there must be a reason why you cannot, and then you would discover something interesting and profound about nature. And then the question would be, is that the end of quantum computing? And then we argue, no, it isn't, because then you can use this phenomenon that you discovered to build a new class of computing devices using that phenomenon that would probably also have a better computational power. Now, if that can happen, of course, the crypto implications are very interesting. So the quantum crypto, I think, would survive in this, as long as you have, if this new sort of scenario has the violation of Bell inequalities, be it, no matter how you think about it, think about very instrumental way. Whatever happens between the devices is up to interpretation. But if the devices respond in a certain way, then you can show, regardless the underlying physical explanation to a large extent, that there could not be a leak of information. And well, again, there will be certain assumption, of course. So, but what exactly that would mean for public key cryptosystem and cryptography, then, Deepankar, I really don't know. It's actually a good question. One would have to just probably more problems will be solved in polynomial time. One would have to just probably revise the whole field of the post-quantum crypto.
Okay. Thank you, Artur, for the very lucid talk.
Yes. So, since we don't have any further questions, just wanted to ask a quick provocative question, Artur. What is your personal view on sometimes what we would say is the hype on quantum technology?
There is a hype, no doubt about it. I think it's and it is something that I'm a little bit concerned of, but certainly it's good that people are fascinated about the whole thing. Sometimes my worry is maybe for wrong reason, or people have too high expectations for quantum, or think that those devices will be available soon. I don't know how long it's going to take to build a quantum computer that can really be truly useful. And it's certainly not tomorrow, it's certainly not in 2, 3, 4 years. It probably will take much longer. And the worst case scenario, of course, is that the bubble will burst and many who invested in quantum computing will be deeply disappointed, and the academia will be left to blame and collect corpses, So that's the worst case scenario. The good, the best case scenario is that the people will invest in quantum technologies. There will be a genuine progress, which there is, there is a genuine progress there.
Okay.
And eventually everyone will be happy, because sooner or later, people will benefit from those quantum technologies. So I think that that what will happen will be somewhere in between. There will be probably many startups that will fail miserably because they overestimated the use of quantum technologies or on a shorter time scale. But also there will be those who wisely invest and will persevere and see the benefits of this investment. So I will certainly not discourage anyone if you have money and just want to invest in quantum, invest in quantum. But I think expectations should be managed. I think there's need for better education, what quantum technologies can really offer.
Mm-hmm.
But again, sometimes there is this cultural divide in business. Quite often it's not what you can factually produce, but what are the expectations of others that you can produce. So,
Right.
So as a collective, there's a slightly different dynamic. So if you want to speculate on quantum, by all means do so. As a scientist, I would just say, be careful.
Sure. So thanks a lot. I think, so thanks once again. I think there are no further questions. So I would officially end this, and thank you for this very stimulating talk. And I'll stop the recording in this case.
Yeah.
Yeah.
Thank